You probably think Pluto is far but reachable, and Proxima Centauri is the next star over, something we might reach once rockets get better. But that image breaks the moment you look at the actual numbers. Your brain is fine with kilometers across a city or a country. It fails completely at billions of kilometers, and it has no built-in sense at all for light years. So let's be direct. Just look at the distances and see why those alone already make Pluto hard and Proxima basically out of reach for our current civilization. Start with Pluto. It orbits about 5.9 billion kilometers from the Sun, roughly 39 times farther than Earth. It also moves on a stretched, not perfectly circular path. But any real mission is going from Earth to Pluto, and Earth is moving too, so the separation between Earth and Pluto is not one number. It swings between about 4.3 and 7.5 billion kilometers. Depending on where each one is in its orbit around the Sun, that swing matters. You can't just decide go to Pluto now, you need a launch window when their positions line up well, or you waste huge amounts of energy and time. Even in a good window, you're still crossing billions of kilometers in empty space with no refuel, no repair, no emergency landing. Every gram of fuel and hardware is loaded at launch and has to last the whole trip. Now look at light, which actually gets to travel at the cosmic speed limit, around 300,000 kilometers per second. Even moving that fast. Sunlight needs about 5.5 hours to go from the Sun out to Pluto. From Earth, signals to a spacecraft near Pluto still take several hours one way. So even simple communication has a built-in multi-hour delay. You send a command, you wait. You only find out later if it worked. That's how stretched the scale already is, just at Pluto. Here's the key point. If Pluto already sits in a regime of billions of kilometers and hours of light travel, then every step farther out ramps the problem up brutally fast. And Pluto is still inside our solar system, still under the Sun's gravity, still part of the local neighborhood. So what happens when you stop talking about planets and go for the nearest star? Proxima Centauri is the closest star to the Sun, and that phrase sounds harmless, like the next stop. In reality, Proxima is about 4.24 light-years away. 1 light-year is how far light goes in 1 year, roughly 9.44 trillion kilometers. Multiply that and you get around 40 trillion kilometers to Proxima. That is not a bit further than Pluto, that is a completely different scale. Put that against speeds you understand. Say you drive at 100 kilometers per hour, a normal highway speed, and somehow never stop, never refuel, never sleep. At that speed, reaching Proxima would take on the order of tens or hundreds of millions of years. That is not a mission, that is basically forever on any human timeline. So you upgrade the speed, you say, forget cars, let's use something like Apollo going to the moon, about 40,000 kilometers per hour. Now the travel time drops, but only to roughly 40,000 years or more. That is still older than any civilization we have ever had, older than writing, older than organized states. Here's the paradox. Proxima is the closest star, and at the same time is effectively unreachable on any timescale that feels like a project humans could actually run. It is not. Mathematically unreachable, you can always say, just wait long enough, but practically it becomes a tens of thousands of years problem. You can see this difference right in the units astronomers use. Inside the solar system, distances are usually given in astronomical units, AU, where 1 AU is the distance from Earth to the Sun, about 150 million kilometers. Jupiter is about 5 astronomical units from the Sun, Saturn about 10 astronomical units, Pluto about 39 astronomical units. The numbers are big, but still in the tens. Once you leave the solar system, almost nobody uses AU anymore. They switch to light years. If you try to use AU, Proxima at 4.24 light years would be over 260,000 AU away, which is a huge, awkward number. So the unit changes, but that shift is also a quiet warning. We're no longer talking about bigger versions of the same thing. We've stepped into a different regime entirely. Why does that unit shift matter for actually going there? because every part of a mission scales with distance. Fuel, power, reliability, communication delay. All of it grows as you stretch the path out. For Pluto, we already need a big launcher, a well-planned trajectory, and a probe that can run mostly on its own for about a decade, while still pointing its antenna accurately enough to send back data from billions of kilometers away. Now take that distance and multiply by roughly 7,000 to reach Proxima. You can't solve that by saying make the rocket bigger. To cover that extra factor, you're not tweaking a design, you're throwing out the whole design and starting again at a completely different level. You need propulsion that can either keep accelerating for years or hit at a large fraction of light speed. You need materials and electronics that can survive radiation and tiny dust impacts over thousands of years. You need navigation that predicts where the target star system will be in the future, not just where it is now. And you need to accept that nobody alive at launch will be alive at arrival. This is why even before we touch the rocket equation, radiation or exotic propulsion, distance alone makes going to Proxima basically impossible for us right now. Pluto is barely within reach for robotic probes, and maybe in an extreme, carefully planted future for humans on a very risky mission. Proxima is not just further than that, it belongs to a different category, one that needs new engines, new materials, new power sources, and probably a much more capable civilization than ours. So the next question is simple and uncomfortable. If distance alone is this bad, what happens when we look at the fastest spacecraft we have actually built and compare their real travel times to Pluto and then to Proxima? The answer makes the gap feel even worse. We've already fired our best space bullets and they barely scratch the map. That's the problem, not a slogan. You've just seen how bad the distances are. Now it's time to ask a much harsher question. What happens when we actually plug in the fastest machines we've ever launched into those distances? The answer is simple. They crawl. So start with one of the big success stories, New Horizons. This is not a weak spacecraft. This is one of the craziest launches we've ever done. New Horizons left Earth at about 16.26 kilometers per second. That's around 58,000 kilometers per hour. At launch, it was the fastest departure of any deep space probe. We threw it off Earth as hard as we basically could with chemical rockets and current tech. Even that wasn't enough on its own. It still needed a gravity assist from Jupiter, stealing a bit of Jupiter's orbital motion to boost its speed further. That trick is what let it cut years off the travel time. And after all that, after a powerful launch plus a huge bonus push from a giant planet, it still took about 9.5 years to reach Pluto. Not to orbit it, not to land there, just to do a single flyby, a quick high-speed pass, grab as much data as possible, and keep going. Think about what that really means. Almost a decade of travel for a one-time shot. If anything went seriously wrong near the encounter, there was no second chance because there's no fuel to slow down and turn around. That's what fast looks like just to get to the outer region of our own solar system. So here's the uncomfortable question. If that's what it takes to do a flyby of Pluto, what happens when you look at the absolute speed champion, the fastest object humans have ever built, and ask if it helps for the stars at all? That's where the Parker Solar Probe comes in. This spacecraft holds the speed record. When it dives close to the Sun, it reaches roughly 690,000 kilometers per hour. That's about 192 kilometers per second. In other words, about 0.064% of the speed of light. By any normal standard, that is extreme. Your everyday intuition is gone at those numbers. 192 kilometers per second is crossing more than 2 Earth diameters in a single minute. But here's the catch. Parker gets that speed by falling deep into the Sun's gravity well on a very specific orbit. It's not a constant cruise speed you can just point at another star. Even if you imagine somehow holding that peak speed and aiming it straight at Proxima Centauri, the timescale is still brutal. At about 0.064% of light speed, a trip to Proxima Centauri would take on the order of 6,500 years or more. That's already many times the span of all recorded human history, just for the one-way trip. So the paradox is clear. Our fastest probe is absurdly quick inside the solar system, but it is practically useless for interstellar travel. The numbers look impressive until you run them against light itself. Once you do that, everything slows to a crawl. So let's do that comparison directly. How bad is the gap between our machines and the speed limit of the universe? Light crosses the distance between Earth and the Moon in about 1.3 seconds. That's so fast you barely have time to blink. New Horizons, at its launch speed, would need around 8 to 9 hours to cross that same gap. Light reaches Pluto from the Sun in about 5.5 hours. New Horizons took years to make that journey. You can see the scale difference immediately. Light treats the solar system like a short hop. Our hardware treats it like an epic journey. Now stretch that to Proxima Centauri. Light needs about 4.24 years to go from the Sun to Proxima. That is already a long wait for a radio signal, but as a travel time for a physical ship, it's actually very good, if you could get anywhere near light speed. New Horizons, moving at roughly 16 kilometers per second, would need tens of thousands of years to make the same trip. Parker Solar Probe at its peak speed still needs thousands of years. This is the key point. We are not almost there. We are not 50% of the way to a practical interstellar speed. We are not even at 1% of the speed of light with a ship that can be used for a realistic mission. Our best deep space probes sit far below that threshold, and the moment you plug their numbers into interstellar distances, you leave the world of missions and step into the world of archaeological timescales. At this point, the obvious reaction is, fine, just make it faster, build stronger engines, burn more fuel, push harder. Why not? We've scaled up technology before. We went from the Wright brothers to supersonic jets in decades. So why not do the same jump in space? The answer is that space travel runs into a different kind of wall, not a physical obstacle, but an energy and engineering wall that gets more vicious with every step toward light speed. Every tiny fraction of light speed you add is brutally expensive in energy. Kinetic energy, the energy of motion, scales with the square of your speed. Double your speed, and you don't just need twice the energy, you need about 4 times. Triple the speed, and the energy jumps by a factor of 9. So when you go from pretty fast by rocket standards to a noticeable fraction of light speed, the energy bill explodes, and that energy doesn't arrive for free. With rockets, you're either carrying your propellant with you, which makes the spacecraft heavier, or relying on some external system like giant lasers or magnetic fields, which requires enormous infrastructure. Pushing speed also creates other issues. Heating increases. The ship slams into more energetic particles and dust. Radiation damage goes up and your shielding has to get thicker. Thicker shielding means more mass. More mass means more energy needed to accelerate. Which loops you back into the same problem. Navigation gets harder too. At higher speeds, tiny course errors grow into huge misses over long distances. You need more precise sensors, better guidance, and more reliable control systems, all running for years or decades in harsh radiation. Every time you say just a bit faster, you're not adding one problem, you're multiplying all of them. Right now, with chemical rockets and small electric thrusters, we are already near the practical limit of what you can throw off Earth at high speed in a single shot and still pay for it, design it, and launch it. We haven't even cracked 0.1% of light speed with a spacecraft that can both go interstellar and survive the trip as a meaningful functioning probe. So when you put it all together, our fastest ships are not just a bit too slow, they are off by orders of magnitude for serious interstellar travel. They work for Pluto, they work for the outer solar system, if you are patient. But when you extend the same hardware to Proxima, you leave human timescales completely. And we still haven't even brought in the full mathematical hammer that explains why speed is so hard to push higher. The thing that every rocket engineer lives with every day. If distance stretched your intuition, and our fastest ships already look hopeless against that distance, what does the actual math of rockets say when you ask it for the speed you'd need to reach another star in anything like a human era? You're about to meet the piece of math that quietly ruins almost every sci-fi starship you've ever seen. And it's not even complicated. It's just rude. It's called the rocket equation. And once you understand what it demands, you see why just go faster stops being a normal engineering problem and becomes good luck civilization. Here's the basic idea stripped down. A rocket moves by throwing stuff out the back. The faster it throws that stuff and the more of it throws, the more its own speed changes. Tsiolkovsky's rocket equation links three things: your total change in velocity, which we call delta V, the speed of your exhaust, and the ratio between your starting mass and your final mass. Starting mass means ship plus fuel. Final mass means ship after you've burned that fuel. The equation says, in simple language, if you want more delta V, you only have two levers. You can make your exhaust faster, that means better propulsion physics, or you can increase your mass ratio, that means starting with way more fuel compared to payload. And here's the part people underestimate: that way more grows exponentially, not in a straight line. Exponential here means this: if you want a bit more speed, you don't just add a bit more fuel. Each extra chunk of delta V demands a bigger and bigger jump in fuel. You quickly end up with a design where almost all of the rocket is propellant, and the actual useful part, the payload, is a tiny fraction stuck on top like an afterthought. That's not a mistake in design. That's what the math forces you into. So the obvious question is, how bad is this for real missions we've already done, like Pluto versus what we'd need for Proxima? If Pluto is already hard in delta V terms, what happens when you dial it up to even a modest fraction of light speed? Getting to Pluto with a flyby already cost a lot of delta V when you look at the full path. First, you have to fight out of Earth's gravity well, then you have to get onto a trajectory that climbs away from the Sun's gravity to reach Pluto's orbit. Add that all up, and you're talking tens of kilometers per second of delta V budget, depending on the exact launch and assist profile. That's already right at the edge of what chemical rockets can deliver in a staged configuration. Now compare that to going to Proxima Centauri at just 10% of light speed. 10% sounds small, but light speed is about 300,000 kilometers per second, so 10% is around 30,000 kilometers per second. Pluto missions need tens of kilometers per second. Proxima at 0.1 C needs tens of thousands of kilometers per second. You've just multiplied the required delta V by roughly 1,000. Now plug that into the rocket equation. Chemical rockets have exhaust velocities of only a few kilometers per second, call it 3 to 4 kilometers per second for a typical high-performance engine. When your exhaust is only that fast and your target delta V is tens of thousands of kilometers per second, the mass ratio you need explodes. You'd get numbers that say, start with a rocket mass larger than anything remotely realistic for a tiny payload. Basically a fuel mountain with a small probe hidden inside. The equation isn't being dramatic, it's just telling you you're trying to use a slingshot to hit something on the other side of a galaxy. That's why chemical rockets simply tap out for serious interstellar speeds. It's not that they're badly designed, it's that the physics of hot gas shooting out the back at a few kilometers per second is nowhere near enough when you want delta V in the tens of thousands of kilometers per second. The gap is too big. So then you say, fine, what if we're clever? What if we stack stages the way we did for Apollo and New Horizons? Does that save us? We already cheat the rocket equation by using multi-stage rockets. You burn the first stage, it empties its tanks, becomes dead weight, so you drop it. Now your second stage, with its own fuel, is pushing a lighter vehicle. That game continues and it works very well for getting off Earth and into orbit, and then giving a spacecraft its big departure burn for a mission like Pluto. That trick is what got us to the moon, and what got New Horizons enough speed to head for the outer solar system. Staging is powerful, but it does not magically cancel the rocket equation. It just helps you manage it. Every stage still has to obey the same exponential relationship between delta V, exhaust velocity, and mass ratio. For Proxima level delta V, even if you imagine a pure rocket approach, you'd need so many stages that the whole structure becomes ridiculous. You're now picturing something like a small mountain of fuel tanks, stacked and strapped together, just to throw a modest payload toward another star. And even that mountain is mostly fuel to push more fuel, which then gets dropped, layer after layer, before the final tiny useful part of the craft is free, so you end up in a dead end. More stages help, but they don't change the underlying fact. As long as you're using stored propellant that you carry with you, and exhaust speeds in the few kilometers per second range, the exponential curve crushes you for interstellar speeds. At this point, a reasonable next move is, alright, then stop using chemical rockets, make the exhaust much faster. That's where ideas like nuclear rockets enter the picture. If the problem is that exhaust is too slow, raise the exhaust velocity and the math gets better, right? Nuclear thermal rockets do improve the situation. Instead of burning chemical fuel, you use a nuclear reactor to heat a propellant, usually hydrogen, and shoot it out the back at higher speed. You might get exhaust velocities roughly double or triple what chemical rockets can do. That raises your specific impulse, so your fuel is used more efficiently. Nuclear electric systems go further, using a reactor to power ion or plasma thrusters, giving very high exhaust velocities but low thrust. There are also more aggressive concepts like nuclear pulse propulsion, for example the old Project Orion idea, where you literally detonate small nuclear bombs behind a pusher plate to drive the ship forward. In theory, that could produce exhaust that is much faster than chemical or simple nuclear thermal rockets, maybe an order of magnitude better or more. Now, all of that sounds amazing until you run it through the rocket equation again. Even if you multiply the exhaust velocity by 10, which is extremely optimistic compared to current tech, you're only smoothing the exponential curve, not removing it. The required mass ratio for, say, 0.1 C is still enormous. You've gone from completely insane to still so bad it breaks practical engineering. You also run into new problems. The more extreme the propulsion, the harder it is to build, control and shield. Nuclear systems add radiation hazards, reactor mass, heat rejection issues, and in the case of nuclear pulse concepts, serious structural stress. You might claw your way to higher delta V, but not to the point where a large, crude interstellar ship at a significant fraction of light speed looks like a sane project. So the conclusion from the rocket equation is harsh and simple. For Pluto-level missions with flybys or maybe orbits, our current technology plus gravity assists can just about manage the needed delta V with a huge but buildable rocket. For Proxima at even 10% light speed, no engine we have, and no near-term nuclear upgrade gives you a usable mass ratio for a big ship. The math doesn't care about optimism, it just keeps saying no. And notice, we've only talked about speed and fuel here. We haven't talked about how long missions take compared to a human life, or how you keep a spacecraft or a crew functioning over decades, centuries or more. If the rocket equation is the math that blocks your first step, then time is the thing that waits behind it, ready to crush whatever barely gets through. So the next question is this. Even if you somehow pay the rocket equation's brutal price and get a ship moving fast, what does that look like on a human timescale, on a civilization timescale, and what does that do to the idea of going there at all? If you launched a ship to Proxima Centauri today, nobody alive on Earth right now would see it arrive. Not their kids, not their grandkids, maybe not even their language or their culture. That's the scale problem once you mix distance with real human lifetimes. The numbers stop fitting inside a normal story. Look at Pluto again, because even that already stretches patience to the limit. New Horizons, with one of the fastest departures we've ever given a probe, took about 9.5 years just to reach Pluto, and that was for a flyby. It screamed past, grabbed images and measurements for a short window, and then it was gone, heading deeper out. There was no slowing down, no going into orbit, because that would have demanded a lot more delta V, which means a lot more fuel, which means a much bigger and more expensive launch vehicle than we were realistically going to build. If you wanted to actually orbit Pluto, you'd have to arrive slower, or burn a huge amount of propellant to break into orbit. That extra braking delta V either lengthens your travel time or blows up your mass budget. You don't just add a small tank and call it a day. the rocket equation fights you again. A proper Pluto orbiter is possible in theory, but you're instantly talking about more complex trajectories, gravity assists, and mission plans that run longer and cost more. And you can't do this whenever you like. Launch windows to Pluto aren't like scheduling a flight to another city. You need the right alignment between Earth and Pluto, so your spacecraft can use an efficient path. Miss that window and your travel time rises, or your fuel requirement jumps. That's why we don't pop over to Pluto every few years, even with. Our best tricks, a one-way trip is close to a decade, and the whole mission, from planning to end of operations, eats a big slice of a working lifetime for the scientists and engineers involved. So that's the easy case, an outer solar system target, still in the sun's grip, still reachable in under 20 years total travel time with a very aggressive probe. Now apply the same kind of speeds to Proxima Centauri and see what happens. Take Voyager-style speeds as a reference. Voyager 1 is cruising at roughly 17 kilometers per second, a bit over 60,000 kilometers per hour, similar to New Horizons' early speed. That's great for leaving the solar system, but on an interstellar map it's crawling. At that velocity, to cross about 40 trillion kilometers to Proxima Centauri, you're talking on the order of 70,000 years of travel time, give or take. That's not a rounding error, that's the number. 70,000 years ago, Homo sapiens were around. But there were no cities, no writing, no recorded history, just small groups of humans scattered around the planet. A probe launched back then, at Voyager speed, would still not be at Proxima now. Faster conceptual probes using existing propulsion ideas, like high-power ion drives or solar sails pushed by sunlight alone, might cut that down to tens of thousands of years if you design them well. That's still way beyond any continuous human institution we've ever run. So you reach a point where calling it a mission stops making sense. Missions are things that people plan, execute and finish within a human timescale. 10,000 years, 50,000 years, 70,000 years. That's geological time. Continent shift. Ice ages start and end. The idea that a single engineered object with moving parts and electronics will survive that long even if nobody is on board is already pushing past what seems realistic. This is where people usually pull out the sci-fi backup plan, the generational starship. The idea sounds simple. You don't need one person to live 70,000 years. You send a self-sustaining community. People live, have kids, die, and the ship just keeps going century after century, and on paper, it dodges the lifetime problem. In practice, it opens a whole new trap, because now your main risk is not just physics, it's sociology. To make a generational ship work, you need a closed ecosystem that runs for centuries or millennia without resupply. That means air, water, food, waste recycling, agriculture or synthetic food production all bounce so that nothing crashes. We have never run such a system for even 100 years. The ISS is heavily resupplied. Biosphere 2 struggled in just 2 years. Now stretch that to hundreds of years, maybe thousands, with no backup. On top of that, you need a social system that doesn't collapse, revolt, or simply decide it doesn't care about the original mission. You're asking a small population to live in a confined environment, generation after generation, under artificial rules, with limited freedom, limited resources, and no outside world. You have to handle education, conflict, mental health, inequality, governance, culture drift, and the simple fact that after enough generations, the people on board might not accept that their lives exist mainly to deliver some future descendants to a star that they will never see. This isn't physics hard, it's civilization hard. We have no data that we can keep a small human society stable for thousands of years inside a metal can. We can't even keep nations stable for a few hundred years without major upheavals. So when you run the numbers on travel time and then say we'll just use a generational ship, you're not solving the problem. You're swapping a known physics problem for an unknown massive sociology and psychology experiment with no test run. Fine, you might say. Skip the society problem. Don't keep them awake, just put people to sleep. Cryosleep, suspended animation, deep hibernation, whatever you call it. Show a crew lying in pods, skip the boring centuries, wake them up at arrival. This is another classic sci-fi patch, and right now it has almost no support in real human biology. We can cool people down for surgery, we can use therapeutic hypothermia for hours or maybe a couple of days in medical settings. Researchers can freeze some types of cells and small tissues and thaw them later. A few animals in nature, like some frogs or insects, can survive freezing conditions for a season. But we do not have a way to freeze a human for decades, let alone centuries, and then reliably bring them back without lethal damage to the brain and organs. Even the cutting-edge work in organ preservation is struggling to extend safe storage times from hours to days or maybe a bit longer. Nothing today points to a practical sleep for 5,000 years wake up fine technology. There's no prototype, no partial success, nothing close. It's not like being 1 or 2 engineering steps away. It's a completely different level of control over biology that we just don't have. Life extension is improving, sure. Maybe we'll push healthy human lifespans past 100, 120, maybe beyond that with serious breakthroughs. But pushing that to thousands of years in a stable, reliable way is a different game. Plus, a longer life doesn't solve radiation exposure, accumulated damage from microgravity, or the psychological load of being stuck in a steel environment for centuries. So you can't responsibly design a mission around biology that doesn't exist yet. We'll invent cryosleep later is not a plan, it's a wish. We'll make humans live 1,000 years and stay sane in deep space is the same. Right now, the only things we know how to keep working for decades in space are simple robotic probes, and even they degrade slowly and lose instruments over time. That's the bottom line for time versus human lifetimes. Pluto already pushes the limit of what feels like a direct connection between launch and payoff. A decade is long, but still human. Proxima, at our current or near future speeds, explodes past that limit into timescales where human crews, human societies, and even human biology as we know it simply don't map onto the journey at all. And all of this, all the lifetime and society talk, is still assuming you somehow have a ship that can push to those speeds and keep going. But we don't. Our propulsion systems are built for planets and maybe for the outer solar system. When you ask them for interstellar performance, they fail completely. So the next pressure point is obvious, even if we accepted. Insane mission durations. Can we even build the engines and power systems to move a ship the way these missions would demand? Your starship isn't missing a paint job, it's missing a power plant type we haven't built yet, and that's the real wall, not the hull shape or the interior layout. Distance and the rocket equation already hurt, but when you actually look at the engines we have, you see the blunt truth. They're built for hopping between planets, not for crossing the gap to another star. Start with the workhorses, chemical rockets. These are the Saturn V type machines, the Falcon Heavy type machines, burning fuel and oxygen, throwing hot gas out the back very fast. They give you high thrust, which means a strong push in a short time, and that's exactly what you need to get off Earth, fight gravity, and reach orbit. But they have low specific impulse, which is just a technical way of saying they don't use propellant very efficiently. Yes, a lot of push, but you also burn a ton of fuel to get it. That's fine for escaping a planet or doing a big burn to head toward Mars or even Pluto, but it collapses when you ask for interstellar speeds. To reach even 1% of light speed, about 3,000 kilometers per second, with a chemical rocket, you'd need such an insane amount of propellant that your ship would be almost all fuel tanks, with a tiny payload on top. The mass ratio the rocket equation demands just kills you. You can't carry enough fuel, you can't launch it, you can't afford it, and even if you somehow built it, the structure would be ridiculous and unsafe. So you might say fine. Chemical rockets are for launch, not cruise. Let's use something more efficient once we're in space, something like ion or electric propulsion. These sound futuristic, and they actually work, we've flown them. Ion thrusters, like the ones on NASA's Dawn mission, use electricity to accelerate charged particles, ions, to very high speeds, much faster than chemical exhaust. That gives them a huge specific impulse. They squeeze a lot of delta V out of a small amount of propellant. The catch is thrust. The push they generate is tiny, so small you could literally counter it with the force of a sheet of paper in your hand. You turn them on and nothing dramatic happens in the short term. But run them for months or years and the effect adds up. They're great for slowly changing orbits, spiraling around planets, nudging a spacecraft over long periods inside the solar system. They're not great when you say, I want to hit a large fraction of light speed in a reasonable time. The power you'd need to drive big ion engines at that level is huge. The thrust would still be low, and your trip times to Proxima would still sit in the many thousands of years range. Efficient, yes, but far too gentle for serious interstellar flight. So then the next thought is obvious. We need engines that use energy from something denser than chemical bonds. We need nuclear. That gives you way more energy per kilogram of fuel, so maybe that fixes the problem, right? Nuclear thermal rockets do look better on paper. You take a nuclear reactor, you run liquid hydrogen through it, heat it up to very high temperatures and shoot it out the nozzle. Because the exhaust is hotter and lighter, it flies out faster, which boosts your specific impulse by maybe a factor of 2 or 3 over the best chemical rockets. That means for the same amount of fuel you get more delta V. Nuclear electric systems go one step further. Use the reactor to generate electricity, then run ion or plasma thrusters at high power for long durations. We've studied these ideas for decades. We've even tested some nuclear thermal concepts on the ground, but we have never flown a full-scale human-rated nuclear spaceship. The engineering is hard. You need reliable reactors, massive radiators to dump heat, strong shielding to protect the crew. The safety issues are even harder. People are not thrilled about strapping a nuclear reactor to a rocket and launching it through the atmosphere, even if you promise it's safe. And all of this is just for missions to Mars and maybe the outer planets. When you actually run the numbers for interstellar speeds, even nuclear thermal looks weak. Doubling or tripling exhaust velocity helps, but it doesn't magically jump you to 10% of light speed with a big ship. The rocket equation still bites, it just bites a little less hard. So the discussion slides into the really exotic territory, fusion and antimatter. These are the engines sci-fi loves, because on paper the energy density is insane. Fusion rockets would fuse light nuclei like hydrogen isotopes, releasing energy the way stars do, and could, in theory, fling exhaust out at thousands of kilometers per second. That's finally in the right ballpark for serious interstellar work. Antimatter is even more extreme. Matter and antimatter annihilate, turning almost all their mass into energy. It is the ultimate fuel in terms of energy per kilogram. The problem is, we don't have controlled fusion running as a regular power source on Earth yet, never mind as a compact, reliable rocket engine. Fusion experiments are huge, complex, and barely holding plasmas together for short bursts. Turning that into a drive system that operates for years in space, under vibration, radiation, and wear, is way beyond where we are. Antimatter is worse. We can make tiny amounts of it in particle accelerators, store it for short times in magnetic traps, and that's it. Producing useful quantities would take ridiculous energy. Storing it safely without it touching normal matter and annihilating is a huge unsolved engineering problem, and building a drive that uses it in a controlled way is another layer on top. These things are fascinating research topics, and they might give us big breakthroughs far in the future, but right now, they are not even close to launch-ready hardware. So then you get to the one idea that actually sidesteps the rocket equation in a clever way: beamed sails. Instead of carrying your energy source and fuel on the ship, you leave the heavy stuff at home and push the spacecraft with light. The concept here is a light sail. A very thin, very reflective sheet attached to a tiny payload. You hit that sail with a powerful laser beam from Earth, or from a station in orbit, or from the moon. The photons bounce off the sail and transfer momentum, pushing it forward. Projects like Breakthrough Starshot suggest you could, in theory, push a gram-scale probe with a meter-scale sail up to maybe 20% of light speed, using a huge array of lasers firing together. That sounds the most promising so far, and it is. But look at what it needs. You need a power infrastructure on a planetary level, maybe gigawatts or terawatts of laser power, which is like having many large power plants dedicated just to this. You need precise control of beam direction so the spot stays on the sail over long distances. You need a sail material that's extremely light, extremely reflective, and can survive intense laser light without melting or tearing. You also have to deal with beam spread, as the beam naturally widens over the distance, with the problem that once the probe gets far away, you can't keep pushing, and you have no way to slow it down at the target. Technically, a gram-scale probe for Proxima at a fraction of light speed might be doable in many decades, if global funding, energy and engineering all line up. Scaling that system up to send a ton-sized probe or a human ship is a completely different league, orders of magnitude harder in power, structure and materials. So when you look across the whole propulsion lineup, chemical, electric, nuclear, fusion, antimatter, beamed sails, the pattern is clear. Everything that actually exists in hardware is good for planets, and maybe for the outer solar system. Everything that could matter for stars lives on paper, in labs, or in the distant future. Your starship isn't waiting on a nicer design. It's waiting on an energy and engine revolution we haven't triggered yet. And even if we woke up tomorrow with a working high-speed engine, strong enough to shove a probe to a big chunk of light speed, that ship would still have to cross real space, full of radiation, particles and dust that all turn deadly at those velocities. So the next question is simple. Even if you solved propulsion, what does the universe itself do to a ship trying to cross it at those speeds? Space isn't empty, it's a shooting gallery waiting for your starship, and the faster you try to move, the more that matters. Distance and speed are one problem, but the environment in between is another. You're not flying through clean vacuum. You're flying through a thin, invisible storm of particles and radiation that never turns off. Start with cosmic rays and background radiation. On Earth, you're protected by the atmosphere and the magnetic field, both of which deflect and absorb a lot of high-energy particles. Outside that shield in deep space, you lose most of that protection. Astronauts on the ISS are already getting hit by a constant stream of high-energy particles from the Sun, from our galaxy, and from distant supernovae. These are not soft X-rays. These are particles that can punch through tissue and damage DNA directly. On 6-month to 1-year missions, this is already a serious health issue. You're talking about increased cancer risk, damage to the nervous system, and potential long-term cognitive problems. Space agencies are working on ways to keep doses within limits for Mars-length missions, which are only a few years total. Now, stretch that exposure from months to decades or even longer. Without very heavy shielding, the total radiation dose becomes lethal, not in a vague way, in a hard numbers way. So any serious long-duration mission, even just to Pluto with humans, needs real protection, not a thin wall and hope. Now look closer to stars, where the environment gets harsher. The sun doesn't just sit there glowing, it spits out the solar wind, a stream of charged particles and sometimes throws. Huge flare events and coronal mass ejections, which are giant blobs of high-energy plasma. Parker Solar Probe's whole job is to dive into that region and measure how bad it really is. Out there, particle energies and densities can spike, magnetic fields twist and snap, and conditions go way beyond what satellites in Earth orbit experience. You want a human ship, or even a delicate high-speed probe, to plunge through regions like that at serious speed and survive it for years? Suddenly, every part of the design becomes an engineering nightmare. Your shielding has to deal with both the normal cosmic ray background and these violent bursts. Your electronics need to handle constant particle hits without flipping bits or burning out. Your life support has to work even when the outside world is throwing radiation storms at you. And remember, all of that is still inside a star's neighborhood before you've even hit interstellar cruise. Then there's the interstellar medium itself, the thin gas and dust between stars. At low speeds, it's basically harmless, a very sparse mix of hydrogen atoms, helium and tiny dust grains. At 10 to 20% of light speed, everything changes. A single dust grain that would be nothing at normal speeds now hits like a tiny bullet. Hydrogen atoms, individually, don't sound scary, but at those speeds their impact energy is high enough that over time, they act like a continuous sandblaster on your hull. Over light years of travel, those impacts add up. They erode surfaces, heat the front of the ship, and can gradually damage or destroy exposed systems, like sensors, radiators, and antenna structures. If you don't protect the leading surfaces, they slowly get chewed away. If you do protect them, you're adding armor, and armor means mass. There's no free move here. Either you accept a high risk of death by dust, or you build serious shielding into the design. This leads straight into the shielding versus mass trade-off, which is another lose-lose situation. The more shielding you add, the safer you are from radiation and high-speed impacts. But every extra centimetre of metal, water, plastic, or specialised material you add to block radiation increases the mass of the ship. And the moment you increase mass, you make it harder to accelerate, harder to decelerate, and more demanding on your propulsion system. For a decades-long human mission to Pluto, if you want to keep radiation doses near current safety standards, estimates quickly climb into many tons of shielding per person, especially if you rely on simple passive materials like water or polyethylene. For a centuries-long or longer mission to Proxima, the numbers get even worse because the total dose accumulates over time. Active shielding ideas, like magnetic or electric fields, are still experimental and have their own power and engineering issues. All of that extra mass goes straight back into the rocket equation nightmare. More mass means more propellant to get the same delta V. More propellant means bigger tanks, stronger structures, and more complexity. Bigger structures are more of a target for micrometeoroids and dust. It's a loop and not a friendly one. So when you imagine an interstellar ship, you can't just picture a sleek, thin hull cruising through clean space. In reality, it has to be a bunker, armoured and shielded against constant radiation and high-speed particle impacts, and that bunker then has to be pushed to absurd speeds by an engine we don't have, using fuel we can't store, for a time span that doesn't fit inside a human life. And even if you somehow build that overprotected, overpowered machine, it still has to know where it is, where it's going, and how to talk to the civilization that launched it, across distances where even more light takes years. So the next problem is obvious. If space is this hostile-y, and the ship is this far away, how do you steer it precisely, and how do you stay in contact with it, without losing it in the dark? Even if you somehow built the ship and gave it the speed, talking to it and not missing the target is its own horror show. Distance doesn't just stretch travel time, it stretches communication and navigation into something that barely fits inside human systems. Start with light time. At Pluto, a radio signal takes roughly 4 to 7 hours to get there, depending on where Earth and Pluto are in their orbits. That's already enough that nothing is real time. If something goes wrong, you send a command and wait hours just to see the result. It's like trying to drive a car with a multi-hour delay between turning the wheel and seeing the car respond. Now jump to Proxima Centauri. A message takes about 4.24 years the one way. Not hours, years. A round-trip conversation is almost a decade. You cannot joystick an interstellar craft. You cannot quickly patch a bug. Every software update is basically a time capsule prepared years earlier, sent into the dark, and by the time you see what it did, the situation on board might be completely different. So that forces a hard rule. The ship has to be heavily autonomous. It has to detect problems, diagnose them, and fix them on its own, with no human in the loop most of the time. And that autonomy has to work correctly for decades or centuries in a hostile environment with hardware that is aging and sensors that are slowly degrading. You're not sending a drone, you're sending a robot mission control. Now think about sending data back. To get useful information across light years, you don't blast radio in all directions, that would spread out and become undetectable. You want a tight, focused radio or laser beam aimed directly at Earth. From the spacecraft's point of view, Earth is a tiny moving dot orbiting the Sun, and the Sun itself is orbiting the galaxy. Over light-year distances, even a tiny pointing error measured in microradians can move your beam off target so much that it sails past Earth completely. That means the ship needs star trackers, gyros, and clocks that stay precise for decades, along with software that constantly updates where Earth will be, not just where it was when you launched. And Earth has to aim back just as precisely if we're using lasers to send commands or power. Two moving platforms separated by trillions of kilometers, trying to keep narrow beams locked onto each other for years with no instant feedback. That's not just hard. That's the edge of what precision engineering and long-term stability can even mean. Then there's the raw signal strength problem. New Horizons, way out past Pluto, already talks to us with a painfully slow data rate. We use giant deep space network dishes on Earth, and even then, downloading a set of images can take hours or days. That's at distances of a few billion kilometers. Now scale that out to Proxima, roughly 7,000 times farther. The power of the signal at our end falls off as 1 over distance squared. Multiply the distance by 7,000, you weaken the signal by about 7,000 squared, which is around 49 million. You're not just a bit weaker, you're orders of magnitude weaker. To compensate, you either need a much more powerful transmitter on the ship, which means more power generation, more mass and more heat to dump, or you need absurdly large receivers on our side, way bigger than anything we have now. Even then, your data rate is going to be glacial. Forget streaming video. You'll be happy with a handful of bits per second, maybe even less, and you'll treat every single image or sense or reading like treasure. So just to talk to the probe, you're building mega-scale infrastructure on Earth, and designing electronics on the spacecraft that can aim, transmit, and receive at tiny power levels for decades, while being constantly hit by radiation. And that's still not the end of the navigation problem, because the galaxy itself doesn't sit still. Stars orbit the galactic center. The Sun is moving. Proxima Centauri has its own motion. Over thousands of years, their positions relative to each other shift. If you aim your ship at where Proxima is now, you miss. You have to aim at where it will be when the ship arrives, which means calculating its future path, including gravitational tugs from other stars and objects, and then trusting that your model holds up over a huge timescale. Any error in your initial trajectory, even a tiny one, grows and grows over the trip. With a 40,000-year mission, a small misalignment early on can turn into missing the entire star system by a massive distance. And remember, you can't correct it easily from Earth, because your commands arrive years or decades late. The ship has to notice its own drift and fix its own course, using limited fuel and aging thrusters. So navigation becomes a game of prediction plus autonomy. You plan for a moving target in a moving galaxy, you launch, and then you hope your onboard systems are smart enough and tough enough to keep the ship on track without constant help. There is no full dress rehearsal for that. You can't simulate tens of thousands of years of flight in real time before you go. All of this is just for a robot. Once you start talking about humans, these navigation and communication limits pile on top of everything else. You can't call home for help when something breaks. You can't get new procedures from ground teams in any meaningful time. The crew becomes its own mission control, engineering team, medical system, and society, all cut off by years-long light delays. And that leads directly into the next layer of difficulty. Even if you could steer the ship, aim the antennas, and live with decade-long message delays, you still have to keep human bodies and human ecosystems functioning in that metal can for years or centuries with no resupply and no escape. That's not just a technology test. That's a question of whether we can build a tiny artificial world that never fails. A human starship is basically this question. Can you build a small planet that never breaks, never runs out, never goes crazy, and then shove it into deep space for decades or centuries? That's what life support actually means at interstellar scale. It's not just air tanks and a water filter, It's an artificial world that has to work better than Earth has ever managed. Look at our best testbed, the ISS. It sits just a few hundred kilometres above Earth, still inside the protection of the magnetosphere, still close enough that a cargo ship can show up in a few hours. And even there, with constant resupply, we fight problems all the time. Mould grows in corners, filters clog, valves wear out, tiny air leaks show up. CO2 levels creep up if scrubbers misbehave. Water recycling systems glitch and need repairs. On top of that, astronauts deal with isolation, stress, and all the mental load of living in a confined metal tube. Now strip away the safety nets. No regular supply runs from Earth. No emergency Soyuz or Dragon to jump into if something fails. No easy return in a few hours. Stretch the mission duration from 6 months or a year into decades or longer. Then move the whole system out of a low Earth orbit into deep space where radiation is higher and help is literally impossible. Suddenly every minor issue becomes a potential end-of-mission event. A water recycler that fails in low Earth orbit is a maintenance job. The same failure 15 years into a Proxima mission is a death sentence if you don't have backup hardware and materials. Next problem, closed-loop life support. Right now we can recycle some air and a lot of water. We can scrub CO2, we can split water into oxygen and hydrogen. That's good, but it's not enough for a truly closed system that runs for decades without outside input. Biosphere 2, the big closed habitat experiment in the 90s, is the classic warning sign here. It tried to run a sealed ecosystem with plants, soil, animals and humans. In less than 2 years, CO2 levels swung out of control, oxygen dropped, and nutrient cycles behaved in unexpected ways. And that was on Earth, with full access to spare parts and outside help. Now imagine trying to scale that concept up to a generational ship or even a 30-year mission, where your system has to maintain balance through births, deaths, crop failures, equipment wear, and random surprises. You don't just need a recycling machine, you need a stable, self-regulating ecological system that can handle shocks and drift without tipping over. We do not have that yet. We barely understand how to keep small controlled ecosystems running for a few years, never mind centuries. Food adds another layer. On a long mission, you can't rely on stored rations only. They degrade over time and take up huge volume and mass. You need agriculture or advanced synthetic food production. That means light, water, nutrients, pollination, pest control, and a predictable supply of calories and micronutrients. All of that has to work in microgravity or artificial gravity, under radiation, without real soil, and under constant mechanical stress. Then there's the invisible stuff, microbiomes. Humans don't travel alone. We carry bacteria, fungi, and viruses. They colonize air filters, surfaces, hydroponic systems, and our own bodies. In microgravity and radiation, those microbial ecosystems can evolve in weird directions. Some bacteria become more resistant, some become more aggressive. You need a way to monitor and control that living background without wiping out the helpful species that keep us healthy. We also still don't fully understand what long-term microgravity does to human bodies, even over a couple of years. We know bones lose density, muscles weaken, fluids shift, vision can change, the immune system behaves differently. We're testing countermeasures, like exercise and maybe spinning habitats for artificial gravity, but we don't have century-long data. We have snapshots. Designing a mission around, we hope this doesn't break humans after 40 years is a huge gamble. Now compare 2 levels of difficulty. A human Pluto mission versus a human Proxima mission. A realistic human mission to Pluto already looks extreme. You'd need life support capable of multi-year round trips with minimal resupply. You'd have to keep a crew alive through the outbound leg, operations near Pluto, and the return leg, probably 10 to 15 years total. You need reliable landing and ascent systems in a distant, cold, thin atmosphere, with no quick rescue if anything fails. That alone is orders of magnitude harder than anything we've done. Proxima takes that and moves the goalpost completely. Now your system has to function not for a decade, but for longer than any human institution has ever existed without serious failure. You're asking your artificial ecosystem, your hardware, your social structure, and your medical knowledge to work continuously for hundreds or thousands of years, while cut off from Earth by light-year delays. No resupply, no spare parts beyond what you brought, no new medical treatments arriving mid-mission. That's a different category of problem. It's not tough engineering, topopus. It's build a tiny self-contained civilization in a box and hope it never collapses. We're struggling to keep a small station running in low Earth orbit with constant help. We are nowhere near running a closed, self-sustaining, stable human environment in deep space for even a single generation, never mind many. And remember, all this complexity is wrapped around a physical structure made of actual materials that has to survive constant micrometeoroid hits, dust impacts, thermal cycling and stress for the entire journey. You're not just keeping people alive, you're keeping the shell they live in from being slowly shredded by space itself. So the next question is brutal and simple. Even if you had the perfect life support and the perfect crew, what happens when the hull, the shields, and the external hardware are being sandblasted for decades at high speed by dust and debris? How long does the ship itself last before space just grinds it down? At starflight speeds, dust is shrapnel and gas is sand, and your ship is the thing sitting in front of the sandblaster for years. People imagine big collisions with big rocks, but that's not the main enemy. The real problem is the tiny stuff, the particles you don't even see hitting you over and over again at insane speeds. Even in Earth orbit, where speeds are only about 8 kilometers per second, small debris already chews on spacecraft. Micrometeoroids and bits of old satellites punch little pits in surfaces. The ISS windows have tiny impact marks. Solar panels get slowly damaged. Apollo hardware came through with scars from lunar dust and small impacts, and that was all at orbital or escape speeds that are low compared to what you want for starflight. So we already know this. If you put something in space and move it fast, tiny particles start eating it. Now scale that up. You're not just going around Earth at 8 kilometers per second, you're trying to go to another star at 10% of light speed, around 30,000 kilometers per second. Same idea, hit a dust grain the mass of a grain of sand, but now the speed is thousands of times higher. Kinetic energy goes like velocity squared. If you increase speed by a factor of a few thousand, the energy of the impact goes up by millions. That tiny grain now hits with energy comparable to an artillery shell concentrated into a very small spot in a very short time. It doesn't just chip paint, it creates a blast of plasma and shock that can punch deep into whatever is behind the surface. And it's not one grain. The interstellar medium has dust and gas spread out everywhere. It's thin, but over light years, a ship plows through huge numbers of particles at 10 to 20% of light speed. Every one of those is a hit, a little explosion, or a little sandblasting event. A swarm of micrometric grains over that distance becomes a constant hail of micro-impacts and plasma flashes on your forward surfaces. Right now, for probes and stations, we use things like Whipple shields. That's basically a thin sacrificial outer layer, placed a short distance in front of the main wall. When a small particle hits the thin layer, it shatters and vaporizes into a cloud, which then spreads out before hitting the inner wall. That spreads the energy and makes it easier to stop without punching a hole. That works for current deep space probes and for things like the ISS, because the speeds and fluxes are in a range we can handle with a few centimeters of smart shielding. For interstellar speeds, the same trick still helps, but the scale is completely different. You'd need a very thick, layered system, maybe many meters deep, or even regenerating surfaces that can be worn away and rebuilt. People also talk about active systems like magnetic or plasma shields that deflect charged particles away before they hit. Every one of those defenses costs mass and energy. A thick physical shield is heavy, An active shield needs power and equipment and still probably sits behind some physical structure. And mass is exactly what you don't want more ops, because it feeds straight back into the propulsion and rocket equation problem. The heavier your ship, the harder it is to get it up to speed, the more fuel or beam power you need, the bigger your launch infrastructure has to be. You can't just say we'll armour it more without also saying we'll pay for that with a much bigger engine and a much harder launch. That's the trade. Lighter ships are easier to accelerate, but fragile. Heavy ships can survive impacts better, but are much harder to push. Even if you design the perfect shield so that each individual impact is survivable, you still have to deal with erosion over time. Think of sandpaper. One pass doesn't do much, but thousands of passes take off real material. Your interstellar ship is not fighting one big crash. It's fighting billions of tiny ones that add up. Over thousands or tens of thousands of years, even a mild erosion rate can strip away coatings, wear down armour, damage radiators, and slowly chew off fine structures like antennas and sensor masts. Radiators are especially vulnerable because they need large exposed area to dump heat into space, and that means they sit there catching every particle that comes in. If they degrade too much, you can't get rid of waste heat from reactors or electronics and things start to overheat. Antennas and optical systems are another weak point. You need them to communicate and navigate, but they also need clear lines of sight. Dust hits can scar lenses, crack surfaces, and slowly reduce performance. You can add covers and shutters and backups, but again, every backup is more mass and complexity. So what you really have is a slow race between how fast the universe grinds your ship down and how long you need it to keep working. For Pluto, you can design a probe that lasts a few decades, with reasonable shielding, and accept some damage. For Proxima, you're asking that same basic idea to hold together for thousands of years, at much higher speeds, in a harsher environment. That's not just harder, it's a different scale of problem. And we still haven't talked about the price just to get the ship moving in the first place. Before dust starts hitting, before radiation accumulates, before any of this long-term erosion even begins, you have to climb out of Earth's gravity, out of the sun's gravity, and pay a massive energy bill just to be free enough to aim for a star. The next step is exactly that. What does it actually cost in speed and energy to just leave home in a way that makes interstellar flight even thinkable? Before you even think about another star, you have to climb out of the sun's gravity mountain, and that bill is already brutal. Interstellar talk often skips straight to how fast can we go, but you pay a huge price just to get into a position where go even means anything. First boss fight Earth. To escape Earth's gravity from the surface, you need a speed of about 11.2 kilometers per second. That's escape velocity. Our big rockets, like Saturn V in the past or modern heavy launchers now, are gigantic mostly because they're fighting that one number. Almost all the rocket at liftoff is fuel, just to push a relatively small payload into orbit and give it enough extra speed to start drifting outward. Getting into low Earth orbit alone already takes most of the work. Then you still need additional burns to change that orbit into something heading out of the Earth-Moon system. When you watch a rocket launch, what you're really seeing is a massive, extensive machine throwing almost all of itself away just to give a small piece of hardware a chance to move on to the next step. Second boss fight, the Sun. Even when you're in Earth's orbit, you're still deep in the Sun's gravity well. You're moving around the Sun at about 30 kilometers per second just to stay in orbit. To fully escape the Sun from that distance, you need a heliocentric escape speed of around 42 kilometers per second, so any probe you send outward isn't just leaving Earth, it's also trying to climb out of the Sun's pull at the same time. New Horizons is a good example of how hard we push this. It got a powerful launch, one of the fastest departures ever. Then it used a gravity assist from Jupiter to boost its speed even more around the Sun. Without that assist, it would have taken significantly longer to reach Pluto, or needed a much bigger launcher. Every extra kilometre per second of heliocentric speed is expensive in propellant. Because of the rocket equation, it doesn't scale linearly, it gets worse the more you want. Now look at the difference between go to Pluto and just go straight out. A Pluto mission isn't a straight line shot. You're going deeper into the sun's gravity well in a controlled way, on a specific trajectory, at a carefully chosen time. You're matching orbits, using the sun's pull and planetary positions to your advantage. The spacecraft doesn't simply blast away and disconnect from everything. An interstellar mission needs more than that. First, you need to decisively escape the sun, not just drift outwards slowly. You need enough speed that the sun's gravity won't drag your velocity back down to something pathetic over long distances. Then, on top of that escape speed, you have to add an enormous additional burn to even reach a small fraction of light speed. So your delta V budget isn't Earth escape plus a bit more. It's Earth escape plus sun escape plus tens of thousands of kilometers per second if you're serious about getting to Proxima in less than geological time. All of that has to come from either propellant you carry or beamed energy systems that don't exist yet at scale. Either way, the energy numbers are huge. We try to cheat a bit with gravity assists. A gravity assist is a way of stealing a tiny bit of orbital energy from a planet. You fly past a planet in just the right way, and its gravity bends your path and changes your speed relative to the sun. This is how Voyager and New Horizons got such high outbound speeds without carrying impossible amounts of fuel. It's free in terms of propellant, but not free in planning. Gravity assists demand precise alignments. The planets have to be in the right places at the right times, and your launch has to line up so the probe arrives at the planet on the correct trajectory for the assist. Those alignments only happen every so often, sometimes once in decades for the really good chains, like the one Voyager used. For interstellar trajectories, the geometry gets even more constrained. You're not just aiming to reach Jupiter or Saturn, you're trying to leave the solar system in a very specific direction, toward a star that is itself moving. That means you have to design a path that uses whatever planets you can, in the right order, to bend and boost your trajectory toward that exit vector. You can't just say launch whenever we feel like it. Your entire solar system becomes part of the steering mechanism, and the best windows for high-energy, good direction launches might be rare and tightly timed. Miss one, and you could be waiting years or decades for the next optimal setup or accepting a slower, less efficient path. So before you ever talk about advanced propulsion, exotic engines, or deep space hazards, you're already paying a massive energy tax just to leave home correctly. You need huge, expensive rockets on the ground, gravity assist as timing, and careful trajectory design just to get a probe out to Pluto in under a decade. Now scale that whole launch and escape problem up to the speeds you'd want for Proxima, and it becomes obvious that this isn't just a build one bigger rocket issue. It's a full civilization-level energy and planning problem. And that brings us to the next uncomfortable layer. Even if physics and engineering somehow said okay at all, do money. And human priorities say the same. Or do they quietly kill the mission long before it leaves the drawing board? Even if physics suddenly said sure, go for it, budgets would still laugh at you, and that's the part people don't like to think about. Building an interstellar mission isn't just fighting gravity and radiation, it's fighting bank accounts, election cycles, and what 8 billion people decide actually matters. Look at what we pay for the stuff we already do. New Horizons, the little probe that did a flyby of Pluto, cost on the order of a few $100 million up to around $1 billion by the time you add development, launch, and years of operations. That's for a small robotic spacecraft. No crew, no landing, one main target, one main flyby. Then look at something like the James Webb Space Telescope, a flagship mission in the $10 billion range. And JWST doesn't go to another star. It sits in a stable spot near Earth and looks at distant worlds from here. Those are the price tags just to look. Not to build a giant ship, not to colonize, not to move a city into space. Just to send instruments that send back data. And even those budgets were hard to push through. They took years of planning, arguments, and redesigns. Now, scale to a serious interstellar mission. Not a tiny gram-scale sail, but a robust, reasonably fast probe to Proxima Centauri, something that can launch, cruise, arrive, do science, and send data back over many years. That's already way beyond New Horizons in mass, complexity, power, and operations. Realistically, you're looking at something that could cost as much as, or more than, the entire current annual space budgets of major spacefaring nations stretched across many years or decades. A crewed mission is another level again. Life support, radiation shielding, propulsion, structure, medical systems, redundancy everywhere. You're probably talking about a project that sits in the same cost class as major global infrastructure, wars, or planetary-scale energy transitions. That kind of thing does not happen because one agency wants it. It implies global cooperation, sharing costs and expertise. It implies long-term commitment on Earth. And it would be competing for money with very loud, very immediate problems like climate change, healthcare, poverty, energy, disasters, and everything else that hits voters directly. You don't just need engineers and scientists to agree it's worth it. You need entire societies to agree to park a huge chunk of resources into a project that will not pay off for many. Decades, maybe centuries, and that most people will only ever see as a distant picture on a screen, if that. Then there's the ethics side. If you're sending hardware to a potentially habitable exoplanet, you can't ignore the contamination question. Do you risk dropping Earth microbes into another system that might have its own biology or its own pre-biological chemistry? Even closer to home, landing humans on Pluto or on icy moons and Kuiper Belt objects raises real questions about contaminating environments that are scientifically precious, that might tell us about the early solar system or about prebiotic chemistry. Planetary protection rules already affect Mars missions. We sterilize parts of landers and rovers. We restrict where they can go if there's a chance of liquid water. For outer solar system bodies, those conversations are only going to get more serious. For exoplanets, you're talking about completely new levels of ethical debate. Are we allowed to throw hardware, and maybe microbes, at another world that we can't clean up if we regret it later? Policy and law move slowly and cautiously here, and they can slow you down as much as physics. Before anyone signs off on a "let's fire a probe at a potentially habitable planet" plan, there will be international meetings, treaties, and arguments. Some people will say, "Go, this is progress." Others will say, "Stop, this is reckless." That debate alone could take longer than building the probe. The companies that build the hardware might not exist anymore when the first data arrives. This is why when people say, "We'll just decide to go to Proxima one day," they're skipping over the hardest part. It's not just about having the technology, it's about having the money, the will, the framework, and the public support to keep that project alive, longer than any current program we've ever run. And the cruel twist is, even if you somehow win that financial fight and you convince a whole planet to commit to an interstellar mission, you still have to build something that works the first time with no full dress rehearsal and then keeps working for longer than any machine we've ever made. That's where the next problem hits, the one where reliability, testing, and one-shot missions collide. You can't test an interstellar ship the way you test a car. You only get one shot per century, and if it fails, that's it. You just threw a generation's worth of money and effort into deep space with nothing to show for it. That's the core problem, not just building the ship, but trusting it. For timescales we've never dealt with before, look at what we actually know about long-duration reliability. Most spacecraft are designed for missions that last a few years, maybe 10 or 20 at the ambitious end. Even then, we budget for failures. Instruments die early, wheels jam, antennas get stuck. We accept that. Voyager 1 and 2 are the classic exceptions. They've been running for nearly 50 years, which is incredible, but only if you ignore the details. Their power is fading. Instruments have been switched off. Glitches keep happening, and teams have to nurse them along with workarounds. They are limping, not cruising. And 50 years is still nothing compared to the thousands of years you'd be asking of a Proxima probe. Now take that timescale and ask it a simple question. How do you test for it? You cannot do a full dress rehearsal of a 10,000-year mission. You can't build a prototype, run it for 10,000 years and then say, okay, version 2 will be the real one. At best, you simulate, you model, you run accelerated aging tests on materials, you test subsystems in harsh conditions, you stack redundancies, but you will never actually see the entire system behave over its full planned lifetime before you launch it. You're always guessing about the long tail of failures. That's a terrifying design problem, because you only find out if you were right centuries later, when nobody who made the decision is alive. Software and hardware make this worse. Code has bugs, it always does. Hardware drifts out of spec over time. Capacitors dry out. Lubricants fail, solder joints crack, cosmic rays flip bits in memory and can corrupt data or instructions. We already see single event upsets in satellites, where one random particle can cause a glitch that has to be corrected from the ground. Now extend that to decades or centuries with no maintenance crew on board, and light years of delay when you try to send a patch from Earth. You can add error correction, watchdog timers, redundant computers, reboot systems, all of that. It helps, but it doesn't give you a guarantee for 1,000 years. At some point, you're relying on layers of software managing aging hardware with fewer and fewer working backups. If something deep and fundamental goes wrong, there is no roll a truck out and fix it. There is no second chance. And remember, even Pluto-level missions are already at the edge of what we can babysit. New Horizons had a primary mission that was relatively short compared to an interstellar trip, less than a decade to the main event. Even so, teams spent years writing and checking every single sequence of commands, rehearsing maneuvers, building simulations, running fault trees, preparing for contingencies. The entire timeline around the Pluto flyby was rehearsed in detail because there was no chance to redo it. For Proxima, you don't just need careful planning, you need a mission profile that can survive multiple generations of engineers back on Earth. Documentation will have to outlive careers, companies, maybe entire space agencies. Languages change, software tools get replaced, file formats go obsolete. At some point, the people in charge of receiving and interpreting the data might not even be using the same basic systems as the ones that launched the mission. So now it's not just a hardware reliability problem, it's an organizational experiment. Can you keep a mission alive, funded, staffed, and understood across 50, 100, 200 years or more while everything about your civilization keeps shifting under it? We have no example of that working at this scale. We struggle to keep infrastructure and institutions stable for a few decades, never mind centuries. All of that is before you even face the last, hardest wall, the one that doesn't care about budgets or institutions or materials at all. At some point you hit the fundamental limits of physics, the speed of light, the energy cost of going fast, and the brutal math of relativity. That's where Einstein quietly walks in and tells you why your just go faster plan fails at the most basic level. This is where Einstein walks on screen and cancels your warp drive, not out of spite, just because that's how the universe is built. Up to now we've talked about engineering, money, and materials. Here you run into a harder wall, the actual rules of space-time. Special relativity says this very clearly. No object with mass can reach or exceed the speed of light in vacuum. Light can go at light speed because it has no rest mass. Anything with mass always stays below that limit. And as you push an object faster and faster, the energy you have to pump in grows without bound. There isn't a point where you switch modes and suddenly go faster than light. There is no just kick it to warp option. The equations don't allow it. You can think in simple energy terms. The kinetic energy of something moving is proportional to the square of its speed in the low speed limit, and in relativity the exact formula is more complex, but the trend is worse as you get close to light speed. The closer you get to c, the more ridiculous the energy bill becomes, per kilogram of mass. There's no soft ceiling here, it just ramps up harder and harder. Even at 10% of light speed, 0.1 c, The numbers are already brutal. Light speed is about 300,000 kilometers per second, so 0.1 c is around 30,000 kilometers per second. At that speed, each kilogram of your spacecraft carries kinetic energy comparable to detonating many tons of chemical explosive. Scale that up to a 1,000-ton ship, which is modest for anything carrying serious equipment or people, and the total kinetic energy is on par with a large nuclear arsenal. That's just the going forward part. If you actually want to arrive at Proxima and not just scream through the system once and vanish into the dark, you also have to slow down. That means you're not just doing one colossal energy project to accelerate the ship, you're doing another colossal energy project to decelerate it, or you have to rely on some external braking method like magnetic sails interacting with interstellar gas, which is another layer of technology we don't have at scale. So the ship itself becomes a huge, stored energy object. Any accident, any misfire, any uncontrolled collision at those speeds isn't just a crash, it's the release of that massive kinetic energy. The system you build has to handle that safely, repeatedly, without melting itself or shredding its structure. Then there's time dilation, the thing sci-fi loves to bring up as the fix. Relativity does say that as you move close to light speed, time on board the ship runs slower compared to time back on Earth. So the crew might experience, say, 10 years, while decades or centuries pass at home depending on the speed. That sounds like a cheat code, but here's the catch. You only get serious time dilation once you're very close to light speed. At 10% of light speed, time dilation is real, but small. The difference between ship time and Earth time is not enough to turn a 40,000-year trip into a comfortable single-lifetime cruise. To really shrink subjective travel times, you need speeds like 90%, 99% of light speed. And at those levels, the energy problem explodes again. You're back to needing absurd amounts of energy per kilogram, far beyond anything we can currently harness or store in a practical vehicle. So time dilation does help in principle, but only after you've already solved the hardest part, getting the ship to those extreme speeds without killing everyone or vaporizing the ship. It's not a free benefit you get to at the speeds we can realistically dream about today. At our current and near-future energy budgets, time dilation is a minor correction, not a turn centuries into decades magic trick. Which leads to the obvious next question people ask: can we cheat the rules themselves? Can we bend space rather than blasting through it in the normal way? That's where ideas like warp drives and wormholes come in. They live in the speculative edges of general relativity, not in ordinary engineering. Warp drive concepts like the Alcubierre metric describe a space-time bubble where space contracts in front of the ship and expands behind it. Inside the bubble, the ship itself never locally breaks the light speed limit, but the bubble moves faster than light relative to distant points. On paper, that looks like a workaround. In practice, the math demands exotic conditions, like negative energy densities and forms of exotic matter, that we have never seen in usable amounts, if at all. And the total energy required, even in optimistic tweaks, is enormous. Wormholes are another theoretical construct, tunnels in space-time that to link distant points. Traversable wormholes, ones you could actually travel through, also need exotic matter with negative energy density to keep the throat open. Again, nothing in our current lab experiments gives us a straightforward way to create or stabilize something like that. Even if a naturally occurring wormhole existed, you'd have to find it, control it, and put one end near Proxima first, which doesn't solve your getting there the first time problem. So right now, these concepts are valuable as math tools. They stress test our theories. They show us what might be allowed or forbidden by general relativity. They highlight gaps in our understanding. But they are not on any serious engineering roadmap. Nobody is in a lab building a prototype warp ring that will fly next decade. They are ideas, not hardware, and they rely on ingredients we don't know how to produce. Put all that together and the message from physics is harsh but clear. You can't go faster than light. Even a moderate fraction of light speed costs insane amounts of energy and creates huge safety issues. Time dilation doesn't help until you're already paying those energy costs. and the exotic shortcut ideas are so far purely theoretical. So if warp drives and wormholes are off the table for now, and normal rockets choke on the numbers, is that it? Do we just stop? Not quite. There is still a whole zoo of exotic concepts, half science, half engineering fantasy that people are poking at. The catch is, every one of them runs into its own wall once you look closely. That's the next step, walking through the sci-fi toy box and seeing why it's still locked. Let's go through the sci-fi toy box and explain why it's still closed, because a lot of the "but what about" ideas sound powerful until you look at the fine print. On paper, some of them bend space, dodge the speed of light, or turn black holes into engines. In reality, every one of them depends on ingredients or control we simply do not have. Start with warp drives, the Alcubierre-style ideas. The basic claim is tempting: don't push the ship through space, reshape space itself. In the Alcubierre metric, you sit in a bubble of space-time. Space in front of you contracts, space behind you expands, and from the outside it looks like you're moving faster than light. While locally inside the bubble, you never break the speed limit. That's the theory. The catch is nasty. To create that bubble, the equations demand regions of space-time with negative energy density, not just low energy, literally negative relative to the vacuum. That's a type of exotic matter we have never produced in any useful amount, in any controllable configuration, and certainly not at the insane scales needed for a starship-sized bubble. On top of that, the total energy requirement, even in optimistic tweaks, is enormous, far beyond our global output. Then there are stability and causality issues. Some analyses suggest the warp bubble would be unstable, prone to violent distortions. Others point out that faster-than-light effective motion can break the normal cause and effect ordering between events, which leads to paradoxes. So right now, warp drives sit in this box labelled mathematically interesting, physically and practically unknown. They're working theory in the sense of the equations allow this form, but they have zero engineering path with present physics and technology. Next toy, wormholes. These are theoretical tunnels through space-time, shortcuts linking distant points. In principle, if you had a stable, traversable wormhole, you could step in near the Sun and step out near Proxima Centauri almost instantly. Sounds great, but again, the conditions are ugly. To hold a wormhole throat open against collapse, you need exotic matter with negative energy density. The same kind of stuff that we do not know how to create at scale. Without it, the wormhole pinches off or becomes non-traversable. We've never observed such matter in nature in a form that would help us here. Even if somehow the universe hands you a wormhole, you still have a big problem: placement. To use it as a Proxima portal, you need one mouth near Proxima already. That means you had to drag it there or create it there, which is back to the original issue. How do you get to Proxima the first time? Wormholes are not an easy startup mode for interstellar flight. They assume you've already won. Then come the really extreme engines, black hole drives, and similar ideas. One concept is to use Hawking radiation from a tiny artificial black hole as a power source or rocket exhaust. Another is to use magnetic sails to brake against stellar winds or interstellar plasma, turning the medium itself into a braking or thrust system. These are fun to model, and there are real papers on them, but the engineering gap is huge. To make a micro black hole, you'd need energy densities way beyond anything we can create. Then you'd have to keep it from evaporating too fast or from eating the surrounding structure, while somehow coupling its radiation into thrust in a controlled way. That's not just hard, it's beyond any material science or control tech we have. Magnetic sails and similar concepts are gentler, but still need gigantic structures, ultra-stable fields, and long operational lifetimes. Nothing about our current space hardware says we're close to that. So if all of these are so far out, why are they still taken seriously by physicists at all? Because they're still useful as science, even if they're useless as engineering right now. These concepts stress test our theories. They show us what general relativity strictly forbids, what it barely allows, and where quantum field theory and gravity clash or leave gaps. When a warp drive metric demands negative energy, that tells you something important about how energy and curvature are linked. When a wormhole solution needs exotic matter, that highlights how unusual stable shortcuts would have to be. In other words, these ideas are like concept machines in a simulator. They're not blueprints ready for a factory, they're tools for exploring the rules of the game. From a launch something this century point of view, they're like concept cars that require roads made of unicorns. Until we have a way to create and control the required exotic matter, or until new physics appears that changes the rules, none of this helps you build a real ship. So where does that leave us? We've knocked down distance, speed, engines, radiation, navigation, life support, materials, gravity wells, money, reliability, and now the sci-fi shortcuts. It sounds like a long list of no, but there's one last angle we haven't talked through yet, what we actually can do next. Because impossible now doesn't automatically mean impossible forever. It just means the timeline is much longer, and the steps are much smaller than people like to imagine. The real question is, what are those steps, and how do they slowly push Pluto and Proxima from fantasy towards something less unreachable? Here's the twist. Impossible now doesn't mean impossible forever. It just means the bill is way bigger than our current civilization can pay. So instead of pretending we're about to launch a Proxima starship, the real question is, what can we actually do next that isn't fantasy, that genuinely moves us a step closer? The first answer is simple. We keep using the outer solar system as our training ground. Robotic missions to Pluto, the Kuiper Belt, and beyond 100 astronomical units are our real-life lab for deep space operations. New Horizons didn't retire at Pluto. It kept going. Right now, it's far past Pluto, acting as a proto-interstellar probe, drifting out into the outer darkness, still sending data home. Every little problem it has is useful. Every instrument failure, every power drop as its plutonium source weakens, every navigation correction when its antenna drifts a bit off target. All of that teaches us how hardware ages in the dark, cold, low-power conditions that any interstellar mission would live in. We're learning how long electronics last, how often you can safely update software, how antennas behave when you're billions of kilometers away. None of this looks dramatic, but it's the baseline experience we're missing. So the obvious next step is send more things out that far. On purpose, probes to the Kuiper Belt, to 100 astronomical units, 200 astronomical units, maybe targeted interstellar precursor missions. Each one pushes the distance and lifetime further. Each one forces us to get better at long-term power, long-term navigation, and automated fault handling. Before you do light years, you need to be good at hundreds of astronomical units. We're not there yet. Then there's propulsion. You don't jump from chemical rockets to starships in one move. You climb the ladder, one system at a time. Nuclear thermal test beds are a realistic next project. You test small reactors and high-temperature hydrogen exhaust in space. You learn how to handle heat, shielding, and control. That gives you higher exhaust velocity than chemical, which means better performance for missions to Mars and the outer planets. High-power ion drives are another step. We already fly small ion thrusters, but scaling them up, feeding them with more power from reactors or big solar arrays, lets you slowly build up higher speeds over time. Solar sails using pressure from sunlight let you test ultralight structures and new kinds of trajectories. They're slow to start, but they cost almost no propellant, which is exactly the direction you want to move. Beyond that, small-beamed energy demonstrators are possible. Not a full Proxima laser array, but experiments where ground or orbit-based lasers push small sails in near-Earth space. That forces us to solve beam control, sail materials, and pointing. None of these steps solve Proxima, but each one nudges the numbers our way. Higher exhaust velocity, better power density, more efficient thrust per kilogram of propellant. But to do the really big stuff, like a laser sail that can push a probe to a decent fraction of light speed, you need something deeper. You need civilization-level infrastructure. That means huge, reliable power grids on Earth, on the Moon, maybe in orbit. It means building and operating large structures in space, not a single station or telescope, but whole factories and arrays. If we ever build an interstellar laser sail system, it will only happen after we've industrialized space enough to mine asteroids, refine materials off Earth, assemble huge mirrors and laser arrays in orbit or on the lunar surface and run them for decades. That's not a physics problem. We already understand how lasers and mirrors work. It's an economic choice spread out over centuries. Do we decide to pour that much effort into space infrastructure instead of keeping everything locked to the ground? That's the real paradox. The hardest walls in this story are not just Einstein and the rocket equation. They're, can we keep a long-term plan alive across generations? And do we care enough to build tools our great-grandchildren will benefit from more than we will? So where does that leave impossible? Right now, sending humans to Pluto at all is barely within reach. It would be wildly risky and extremely expensive, and we would struggle to design a mission that doesn't push our life support, radiation protection, and reliability right up to the edge. Reaching Proxima Centauri with anything bigger than a tiny gram-scale probe in less than many thousands of years is way outside what our technology and economy can manage today. But look at the pattern. Every decade or so, we quietly push the frontier a bit further. Faster probes, better shielding, more autonomous software, bigger and more precise telescopes, more ambitious mission profiles. We went from no satellites to global navigation systems, from first moon landing to remote rovers and helicopters on Mars. From Pluto is a fuzzy dot to high-resolution maps of its surface. None of those jumps made interstellar flight suddenly easy, but if they all changed what counts as obviously impossible. That's how this really moves. Not in one big warp drive reveal, but in a long series of boring-sounding upgrades that stack over generations. So when you hear, we can't reach Proxima with a real ship, that's a description of right now, not a permanent law. The universe is basically saying not yet, not never. The story of the next few centuries is whether we use Pluto, the Kuiper Belt, and the deep outer system as our training ground, whether we build better engines one step at a time, and whether we choose to build the kind of civilization that can afford to even ask seriously about another star. If we don't, Proxima stays a distant point of light forever. If we do, then one day, much later than sci-fi promised, but earlier than never, somebody may look up at that star and know there's a piece of human hardware moving around it because we put it there. This video's for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.